Thank you, Chairman, for the introduction. Now, it's very pleased today to talk to you about some of my work. Before I begin my technical talk, I would like to have 2 slides to introduce the place that I work. I'm coming from the Chinese University of Hong Kong. I don't know whether you have been to Hong Kong or in the Chinese University. This is the place. It looks nice with the lake. And the department that we are working is inside here. So it's Engineering 1, Engineering 2. All the engineering departments are housed inside these 2 buildings. And the department within these 2 buildings are electronics department, computer science, which is the department that I'm now working. Starts from 73, information engineering, system engineering, etc. And we have about 100 something faculty members and 2,000 undergraduates, 8,000 postgraduates. So it's, we do have a large team of people working in PhDs and etc. Right? So this is the place. So the usual image of Hong Kong is very crowded, but it's not in the Chinese University. So if you have time, visit us, visit me. You can find my email me, and then I can take you around and have lunch and dinner together. All right. So so the work that I'm doing, I will introduce in this order. Is actually projector-based system. So what is a projector camera-based system? That is, the system has a projector, and there is a camera looking at what the projection is. And with the interaction between the projector and the input, you will be able to manipulate the input by your own hands. So this is the basic idea. And we have, in the system that I'm presenting, it is only one part of our development. So before I begin with the details, let me tell everybody about the structure of the system. First, we have a projector camera pair. That is the projector with the camera which is next to the projector. And we have an object to display, which is a foam 3D ball. It is a sphere. So the projector is projecting something on the sphere, and also there is a sensing device which is underneath this sphere. So when you rotate the sphere, so it understands how much you rotate it and adjust the projector image accordingly. So if you rotate it in the right, it will project something on the right. So it is more or less like a mouse. Right? But the beautiful thing about this is to directly manipulate the object that you are using for the display. A mouse is usually not considered as the same category, because the mouse, you move the mouse, but what you're seeing is not at the position of the mouse. Now, before I talk about the work that I'm presenting, let me go through some of the previous work that we have done. Now, this is a system that we built for various applications. This is the projector camera system that I described. The first system that we built is a board. It's not a sphere, it's a board that you project image onto the board. So how does it know where the board is? It's by using a computer vision method. The computer vision method is by using the camera here, looking at the board. So using a quadrangle detection algorithm, you can detect the position of the board. Then when you change the position of the board, you project the image according to the position. So you are just, you can move around, right, literally. I'd create this idea when I was flying on a plane, saying that I don't have to look at the screen in the front. I think if I can hold a piece of paper, and if the film is already on the piece of paper, it will be nice. So I developed this. I hope I can give you a demo YouTube that we did in the past. So it's a CVPR paper in the past. So it's a projector camera movable system. There's a basic setup. We are still using this setup. So you can display static images. So if I move it to another place, the image follows. You may observe some time lag, which is a problem in the past. But we are trying to fix the problem by some other means, which is now the current work. Right? So projecting dynamic, you can also project not just image, but also video. Right. So this is the basic idea. Now later on, we have developed using the basic methodology and hardware, but change a little bit so that you can also display 3D objects. Now what do I mean by 3D objects? The projector is 2D, the camera, everything is 2D, the image is 2D, but by manipulating the object, the board, we can see some 3D object. Now this is no 3D at the moment, it's just 2D translation. You can move it around, no problem, but if we add something to the display, change the display according to the rotation of the board, then we can, like that, we can create some kind of 3D display, right? Now, why I developed this is because I thought it will be useful for museum. For example, if you go to a museum, you want to present some object to the student, but you don't want the students to mess around with the object. So what you need to do is to give them each one a board. Then you have a projector projecting the image onto the board. Then you have a 3D display, like a museum item, right? So this is the background for the research. Now, the current development is like this. So we are still using this projector. Now, this is the main part. It's called the motion detector. The motion detector is a very simple device. In fact, if you want to build one yourself, I will show you how to do it with a very low cost. So the idea is to project something onto the sphere. Now, why a sphere, not a board? Because if it is a sphere, if something is just like a sphere, like the globe or the Earth, right? It's a sphere. If you want to look at the one side, USA, China, Korea, then you can rotate whatever you like. But how do you know how much you rotate it? Is by the sensor inside this magical box. So this magical box contains an IR laser, which is a laser pointer like this, but the emitted light is infrared, you cannot see it. And there is an optical chip, which is taken from a mouse. So we bought a mouse, but a high quality infrared mouse, and take it apart, do the interfacing, then we can sense the rotation of the sphere. Now, how it can be done, it is something to do with physics. Now, before we get into the method, let us look at this demo. So now I'm displaying the Earth, right? Well, some kind of Earth. We download it from the Google, and then we can move around, and then so that you can see how it moves. So it is as if the picture is painted on the sphere or the ball, but actually it is only a virtual display from the projector. All right. So this is the idea. There's another display for the arrow. So if you rotate to the left and right and forward and backward, it can sense the direction and just displaying it. Right. So I want to talk about why it can be done in this way. It is by a magical optical phenomena. That is, if you shine a laser source onto an object, it will reflect. Now the problem with laser is because the wavelength is very, very small. So if two object points, two reflecting points are nearby but not at the same height, it will be causing interference at the image. So what you're seeing is the reflection. The interference depending on the surface. So because no surface is absolutely flat, a tiny change of the surface, even a piece of paper, anything like that, will result in pattern like this. So you see a pattern. So if you rotate the object, the pattern changes. Just like you have some object change, you use a camera to sense it. So this is how it is being done. So you have motion, then it changes. We use OpenGL to write the software, and then you project it on the spherical surface. So the experiment is performed using a PC, etc., with the display, motion tracking. So we use a plastic ball as a movable display surface. Our average tracking update rate is very high, it's 1 ms per tracking. Now, to show that this is effective, we did an experiment using a few users. Based on a few users, 6 users, each one were given a task of pointing to a particular position using a mouse or our dynamic sphere. And we found that most of the time using the sphere can result in faster manipulation. So this is an alternative. I cannot say that you can use the mouse, you can use it to replace the mouse. But earlier when somebody presented work about use it for aged people, senior people, I think this can be a useful device. I mean, for aged people, holding a ball is not difficult. When it rotates, it creates some kind of display that will be fun and also quite encouraging for them, perhaps. Right? So these are the demo. Actually, you have seen this demo. So this is also the same demo, I believe. But it's taken from outside, so you can see how it works. The other side is the Earth. Right, so here's the conclusion. We propose a simple but effective handheld spherical display system made from low-cost devices All you need is only a laser pointer and a mouse. Our system consists of two parts: the projection module display the virtual object depending on the motion of the plastic ball. The motion sensor detects the rotation, and then the system displays the images. Now, this is only one part of my research. Actually, we believe this projector camera plus handheld direct interfacing is very useful for future work. We are now currently developing a 6D mouse, which has a gyroscope and accelerometer for sensing the motion, as well as computer vision system to detect the translation. All these can be integrated together. One more I want to say is that I think you all know that Google Glass is becoming very, very popular, or at least it is something that captures people's imagination. Now, I think we can integrate mobile phone, Google Glass all together. If you have a mobile phone, if you have some kind of sensing system which can detect the rotation, translation, etc., using the method that I developed here and previously using the Google Glass, all integrated together will become rather effective and useful for the game playing or education or whatever. All right. So we believe the proposal system is useful in interactive human computing interface, and should find application in many different areas. Future works, as I said before, we are now still currently using the same setup, but develop different means, using KINTEX, everything. So if you have time, come to visit us. I will show you the real thing. All right. There are some references. Yeah. So visit my webpage. This paper can be downloaded from my webpage. Thank you. Any questions?
I just have a
Yeah.
couple of questions. First one is, I wonder that the laser printer that we talked about, is it that you expect through the glass surface, or only like solid surface? It's just like.
I'm not sure about the glass. Because the glass cannot be reflected. It can only.
Yes.
Yeah, it can be reflected. But any surface, if it has reflection, it can be done. So a piece of paper, a piece of board, a piece of plastic, no problem. But glass, I'm not quite sure. I would guess.
Another question is, it's more like a suggestion than question, because I'm not in computer science, I'm in art. So it looks like the sphere has only one direction of the projection, which is kind of, I think is kind of limited the whole the possibility of, because I think your study is very interesting, but if there's another direction of
Sure. Well, my answer is that it is not limited by the method that I use. It's limited by the funding that I have. I mean, combining different projector into one place is a developed field. Many people are working on there, but I'm not sure whether they work on a sphere or not. They probably have worked on a plane surface. You see, if you go to some places, you see many projectors projecting a large screen, extended screen. But for the sphere, I'm not quite sure. Yeah, it's a good idea. I should get more fun to buy more projectors so that I have a totally spherical display.
Yeah, I think that would be more.
Yeah, of course. Yes.
In the video, when you held the ball, it's moved very slow.
Yeah.
And it could be rotate. I saw that, but it moves more faster. Could be rotate.
Yeah, I think same as many experimental systems, it is only a demonstration of the idea. To increase the speed, in theory, it can be done by using a better computer, using a better sensor, that kind of thing. But here I just illustrate the idea.
I also have a question. In your sphere, there were many speckles.
Speckle, yeah.
So did you test with the clean sphere?
Actually, we have tried to use a very, very plain paper, any paper, brand new A4 size paper. You put it there, you see speckle reflection. Speckle reflection is created by a very, very tiny difference in height.
So you did not make the speckle on purpose?
You don't have to make anything, just any surface. A rough surface, a plain surface, to you is plain, but for at the microscopic level, it is not plain at all.
Okay, thank you.
Right, thank you.